Okay, so this is going to be a video of 20 problems approximately, and in this video we're going to really have a look at a few problems that would be unique from whatever the syllabus is for ISI and CME, and I'm just going to list the problems right now so that we can understand what we're going to do in the next period of the lessons. Okay, so let's begin. So the first problem, we're going to look at a basic case of limit n tends to infinity n to the power n upon n factorial raised to the power 1 by n. Now, while solving this problem, I will let you know more than one way to solve it. Basically, there is a way which we all solve, which we high schoolers solve, but there is another way which we can use in order to solve this problem. Some clever way. So this is basically a problem from real analysis, but has been used in many high school books and many J Advanced books. But it obviously does not originate from J Advanced or J Mains or something like that. It's of a very high level difficulty. But using the methods that have been taught, which have really been misleading a bit, this problem has been overstated. So, anyways, we'll see multiple ways to do this. Number 2 is the problem that for a sequence xn, if x0 equals to 1 and xn plus 1 is equal to 3 plus 2xn divided by 3 plus xn, and this holds obviously for all n greater than equals to 0 starting from the next one. We need to find limit n tends to infinity xn, obviously, if it exists. So these are the conditions we need to do. So this kind of problems are very much common in subjective and objective portions. So we're going to look at that. Okay. Number 3. Again, a sequence problem. Most of the problems of limit are mostly sequence problems, and the ones which are not, they would be like basic problems or problems that would require use of logarithms or something like that. So we are going to look at sequence problems more versely in this entire video. So another problem is x naught is 1, and we have xn plus 1 equals to 1 upon 2 plus xn n greater than equals to 0. Prove that xn converges, and yeah, find its value. Find its value. Okay, let's look at a fourth problem right now, and then let's solve the 4 problems, and then we shall proceed. Okay, the fourth problem is a bit tricky. Let's say that the fourth problem we have the same sequence kind of problem. So let's say we have xn plus 1 equals to alpha xn plus 1 minus alpha xn minus 1, and here alpha belongs to 0, 1, and xn be any sequence of real numbers satisfying this relation, and it has a limit. So we need to find an expression for the limit in terms of this alpha x0 and x1. So let's say alpha x0 and x1 is given. Find limit xn. So that's something we need to find here, and for the limit part we need to be very careful because there are certain manipulations that need to be done. Okay, so starting with the problem number 1, which is a fairly basic problem in terms of doing the geometries and sketching out the problem solutions. Still needs to do it. Okay, so first problem, it is limit n tends to infinity n to the power n divided by n factorial raised to the power 1 by n. Now the thing is, If it were an usual class, I would have asked to solve this and take the 5 minutes, but this 5 minutes of each problem, which are used in solving and applying your own creativity, you should be using this at your home while solving the problem by pausing it. And so this video essentially should be much longer, but since I would be not wasting any time in giving you time, because it's very easy to pause, it's not a live class. So you can easily skip that 5 minutes, right? So answer. Now there are multiple ways to solve it. One of the ways, as you know from high schooling patterns, is basically we can just simply take the logarithms and do stuff like that. So that way looks something along the lines of this. So let's say we have the limit L equals to limit n tends to infinity n to the power n divided by n factorial raised to the power 1 by n. And then you simply take the ln, and this entire thing becomes 1 by n limit n tends to infinity, and ln of n to the power n is basically ln of n to the power n by n factorial. So it becomes ln of n to the power n by n factorial. Now using the properties of ln, we can easily write this as 1 by n limit. The limit should be on the left hand side basically. So anyways, ignore the limit. Say there is a limit here. 1 by n. And now there should be n ln n minus ln of r, where we have a summation here, right? From r equals to 1 to n. So limit 1 by n. Now this n ln n can also be written inside the summation, so it becomes basically summation ln of n by r from r equals to 1 to n. So in this way we can, after doing this, we can solve it using the Riemann formula. The Riemann formula essentially states that if you have limit n tends to infinity 1 by n summation r equals to 1 to n, f of r by n equals to 0 to 1 of x dx. But this is not the method we are really looking forward to. We are looking forward to a new method which will be very much useful. So about that method, the method I am going to talk about right now would be along the lines of real analysis. This method is basically trying to observe a new line. So for this problem, what we do here is we assume P1 is 1, P2 is 2 by 1 whole square, P3 is 3 by 2, that's what, whole cube. And similarly, if we go up to Pn, it should be n by n minus 1 whole to the power n. And the thing is, if you do this multiplication, P1, P2 all the way up to Pn, and then divided by n, you get n to the power n by n factorial. Now this Pn is a sequence, right? This Pn is a sequence, and this sequence goes to E. That how do we prove it? Okay, let's do it. So the sequence, the general term of the sequence is this. So limit Pn is basically limit n minus 1 plus 1 by n minus 1, obviously, whole to the power n, right? And you can write this as limit 1 plus 1 by n minus 1 to the power n minus 1 into n by n minus 1, right? And this thing goes to e to the power limit n by n minus 1, which is also 1, so this thing goes to e. So Pn goes to e. Right. Now, since Pn goes to e, then we already have the fact that this product also goes to e. So this is very easy to get, because assuming the product expansions and using theorems of analysis, this is very easy to get that since limit n tends to infinity, Pn goes to some real number x, then the product divided by the expression will also go to the same number. So that's another way of doing it. So it's a bit technical and very useful. So if Pn goes to some number, then this product goes to the same number, right? So that's for problem number 1. Problem number 2. Let's first check out the problem what it was. X naught equals to 1 and xn plus 1 is equals to 3 plus 2 xn divided by 3 plus xn. So first write yourself the problem number 2 of this. So xn plus 1 is equals to 3 plus 2 xn divided by 2 plus xn, right? This is bj, yeah, xn, and x naught is 1. So we need to find the value of the limit xn if it exists, obviously. So there are 2 things. First, if the limit actually exists, then we can simply say that x infinity is equals to 3 plus 2x infinity divided by 2 plus x infinity. This is because of the fact that if limit exists, then we can simply plug it into the recurrence relation. That is valid actually, which should produce you an equation like x infinity squared plus x infinity minus 3 equals to 0. And it shall give you the positive value x infinity equals to half minus 1 plus 1 over 30, which is the correct answer. But the thing is, we also need to prove that the limit and the sequence converges. And how do we do that? So let's start with xn plus 1 minus xn, which is basically 3 plus 2 xn divided by 3 plus xn minus 3 plus 2 xn minus 1 divided by, this is 2 actually, 2 plus, I guess the problem stated as 3 most probably, because 2 doesn't make sense enough. It should be 3, yeah. So 3 xn minus 1. Right. If we do a fresh copy. Yeah, so 3 plus xn and 3 plus xn minus 1. So this is the recurrence relation. Now if you simplify it enough, what you get is that you get that xn plus 1 minus xn is equals to 3 times xn minus xn minus 1 divided by 3 plus xn, 3 plus xn plus 1, n minus 1, sorry, 3 plus xn. So this is basically just going to have some solutions. Now from this it should be pretty much clear that this modulus of this thing this should be very much less than equals to 1 upon 3 of modulus of xn minus xn minus 1. This is because of the fact since we have all these alterations, and this is basically a theorem, a statement which you should learn, which is the Cauchy sequence. The Cauchy sequence, where it will directly follow. I'm not elaborating it here, so this directly follows from it. So the Cauchy sequence has more than 5 parts, which are not hard to study. It's easy to grab from online and compare the answers with you. This is very important because questions of this have been noticed in 2018, where there was a sequence and Cauchy sequence problems, and most of the people never got it right, just because they didn't know the Cauchy sequence and its conditions and the terms that were used in it. So basically, xn plus 1 minus xn will be less than equals to 1 by 3 modulus of xn minus 1. This line, it follows from here. Anyhow, if this follows, then the iteration xn plus 1 minus xn, which is less than equals to 3 to the power minus n modulus of xn minus xn, right? So this basically comes, and obviously if this comes as a result, then we can also say that xn plus 1 xn is greater than equals to all 1 because basically it increases. To be honest, yeah, it does increase because if you assume by induction it increases, then it always increases. So yeah, after x naught, the x value of x1 would be greater than or equal to x, right? Anyhow, and this is a constant c, some random constant c, which is positive, obviously. Now this proves that the sum n equals to 1 to infinity xn plus 1 minus xn, this thing, this basically converges. Why does this converge? Is because this is bounded by this is equals to limit xn minus x1, and this limit xn is basically represented in terms of this infinite series, and this infinite series converges because this terms, the xn minus xn terms, are dominated by the 3 to the power minus n into some constant term. And the thing is that n equals to 1 to infinity, some constant c which is positive by 3 to the power n, this converges. Right? This converges to some 1 by 3 divided by 1 minus 1 by 3, so it converges to some cy something. Problem. It's 1 by 3 divided by 1 minus 1 by 3. This thing is basically this. So yeah, because of the fact that each of the terms are dominated by 3 to the power minus n into the same constant c, so the sum of xn minus 1 plus xn converges, and since it converges, so limit xn is finite, which proves that xn is finite, and indeed the value of xn then would become this value as stated, half into minus 1 plus root over 13. And that's how we prove this problem. Next problem. The next problem says that we have x naught plus 1. X naught is 1 and xn plus 1 is 1 divided by 2 plus xn, and we need to prove that xn converges and we need to find its value. Okay. So let's do this. So first we write down the equation x naught is 1 and xn plus 1. Basically 1 divided by 2 plus xn and n greater than equals to 0. This is 2 plus xn where n is greater than equals to 0. Okay. Now what are the first thoughts when you see this problem? Basically this problem should be a very much groundwork, because there are some things you should understand about this problem. Since x naught is 1, and as we can see from the iteration that each of the terms are positive, so this actually gives great bound for xn. So that bound, first we need to establish that bound. So the bound is basically, since xn is greater than 0, so we can always say 0 less than xn less than half, because this term in here will reduce to half, right? Because xn is greater than 0 and the reciprocal will turn it into a lesser sign. So we can always say 0 less than xn less than half for obviously n greater than equals to 1, because the first term is already defined as 1. And since that's the fact, we can always say that plugging in the value of x naught and trying this x1 thing, you can always say that 2 by 5, because plugging in half gives you 2 by 2 plus half is 5 by 2, which is 2 by 5. So this 2 by 5 should be less than xn plus 1, which is basically equals to 1 by 2 plus xn, which is less than half. And this is another inequality which we can establish. So these are some strict inequalities which we actually can establish out. Anyways, now coming to the problem, we need to find out that what's exactly happening with this. So if we were to take the unique solution, then just like we did before, we just need to do that. Let's say we have limit xn equals to some x, and then we plug in the value of x equals to 1 by 2 plus x and find out the value, which gives which comes out as p equals to root 2 minus 1, right? This is the unique solution, the unique positive solution that this limit might have if it exists. But now, using this, we can actually understand from the fact that we can always find out, again as a similar previous problem, similarly the inequality, some constant c which is less than 1 multiplied by xn minus 1 minus p. We can do this. And then by repeated iterations, it should be c to the power n of x1 minus p. And this actually tells you that the sequence xn plus 1 actually tends to the denoted limit of p. So we can say from this that xn plus 1 tends to p. Again, this exact definition that xn plus 1 minus p, modulus of which is less than or equals to c to the power n times x1 minus p. This gives you a very clear idea that yeah, it obviously tends to p. So xn plus 1 down limit will tend to p, which is root 2 minus 1, and thus it exists. And this is an essence of Cauchy sequence, which I've taught on the channel, and as I said, you could get it. But even from this problem, you can easily get it that if something is in this form, I can tell you a little bit about it, because see, when xn minus p is less than or equals to the c to the power n into some alpha, whatever it is. Now, when you apply the limit on both sides, the thing is, this thing goes to 0 because 0 less than c less than 1, right? So this thing becomes 0. Now, modulus of something cannot be if this is less than 0, but it is also true that xn minus p is greater than or equals to 0. This is already true, but this we got from here, the less than or equals to. And both of this together imply that limit of xn minus p is equals to 0. Or in other words, limit of xn is equals to p. There should be limit both of here, basically. So limit of xn equals to p can be reduced directly from here. So this is basically an application of the Cauchy sequence. Okay, so that completes this problem. Okay, so you see the fourth problem. So xn plus 1 is alpha, xn plus 1 minus alpha, xn minus 1, alpha belongs to 0 to 1. So we have xn equals to alpha xn minus 1 plus 1 minus alpha xn minus 2. Now here, using some different alterations, which I'm skipping just to make the video shorter as much short as possible, because it could easily be in more than 45 minutes video. I'm just making the time short so that you can learn xn plus 1 divided minus x of n. This gives you so this is the relation you might actually obtain while using this kind of solution. Now this thing, basically by the induction principle, again applying that repeatedly and doing the stuffs, you can basically get xn minus x1 is basically alpha minus 1 to the power n minus 1 multiplied by x1 minus x1, and hence the sequence is Cauchy and it converges, as I said. Now if you were to look at the solution, basically this should be xn minus 1, obviously. This solution xn minus xn. Now if you were to look at the expression xn minus x naught, this is again basically a telescoping series, right? Again, telescoping series of the form k equals to 1 to n xk minus 1. But this again equals this x1 minus x0 to the same summation, but alpha minus 1 to the power k minus 1. And from this, we can easily take the limits on both sides, which we can do like this. We can write limit xn minus x naught equals to this x1 minus x naught remains the same, but the index was n, so it becomes an infinite summation, and alpha minus 1 is obviously less than, it lies in the region where the geometric progression is valid, right? So it just gives you 1 minus alpha minus 1, right? So this becomes limit of xn becomes x naught plus x1 minus x1 minus x naught divided by 2 minus alpha, which finally gives you the value 1 minus alpha x naught plus x1 divided by 2 minus alpha, which completes the problem. So basically in the problem you just needed to prove that it was a Cauchy sequence, and a Cauchy sequence is basically proved in the last phase of the problem. So in the next problem you will get another 4 problems, same type. So in the last phase of the problem, I'll just explain to you what the Cauchy means. So if you can prove somehow that if xn minus 1 is equals to some constant c times xn minus 1 minus xn minus 2, and if this constant c is basically 0 less than c less than 1, then you can easily say that xn is a Cauchy sequence. Okay, xn is a Cauchy sequence, and then therefore xn converges. This has been proved before in many textbooks, and this is a standard theorem, so you can use it without even knowing the proof. So that completes this 4 problem video. So the next video will shall contain another 4 problems. So
Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.